Relationships between the free energy, equilibrium constant, and cell potential. This is part 4 of the electrochemistry series. So now let's talk about chemical energy and work. We mentioned it earlier in these lectures, but now we're going to go into a little bit more depth. Now, chemical energy is converted into electrical energy in a galvanic cell, and we've already talked about that. That happens spontaneously, and we can use this energy to do work. Now, the amount of the electrical work is actually the product of the charge transferred multiplied by the potential difference, or the voltage. And you can see the equation for that at the bottom of the slide. Electrical work is equal to volts times charge in coulombs, and that'll give us joules, which of course is an energy unit. So remember that 1 Faraday is the magnitude of electric charge in 1 mole of electrons. And I have just shown that conversion here. So here's our mole of electrons, and there's the coulomb per electron, and that gives us basically the quantity for Faraday's constant. The total charge that is transferred in any of these reactions is the number of moles of electrons times Faraday's constant, so NF. That's our total charge. And moles, N, is the number of moles of electrons transferred for a balanced oxidation-reduction reaction. So that's moles of electrons transferred per mole of reaction, and you have to make sure that the oxidation-reduction reaction is balanced before you determine what N is. And of course, 1 Faraday is 96,485 coulombs. The maximum electrical work done by the cell is represented as W sub ELE. So that tells us that's electrical work. And it is actually related to the measured cell potential. So here's our cell potential and the quantity of work done by the cell divided by NF. And we can rearrange this and get the work defined in terms of the cell potential and the charge transferred. Now this negative sign here is very important. It indicates that the work is done by the system. So in other words, the work is done by the electrochemical cell. Now let's talk about free energy. Now we can redefine free energy in terms of work. And so delta G basically is the energy that's free to do useful work in a chemical reaction. And in this case, that would be our electrical energy. If we substitute our equation that we derived earlier, so the work defined in terms of the cell potential and the charge transferred, and plug it in for delta G, then basically we get that definition for delta G. Negative NF delta E cell, so the cell potential. Now this does not necessarily have to be at standard conditions. Notice we don't have the ought here, but we're going to define it under standard conditions. Now we have the ought on each of these, and that means our concentration is going to be 1 molar. If we have a gas present involved in the reaction, then the atmosphere will be 1 atmosphere, and as I mentioned, usually 25 degrees C. And also remember that delta E cell and just E cell, depending on the textbook you're using, you'll see either one of those, but in this case they just mean the same thing. Now, when delta G naught is negative, remember this from earlier when we talked about thermodynamics, when delta G naught is negative, or delta G in general is negative, the reaction is spontaneous. So when the cell potential, so right here, when the cell potential is positive, then that means the free energy is negative. And so we've already seen that previously. Positive cell potentials mean the cell is spontaneous. Now, let's continue with the free energy and our 2 definitions. In the thermodynamics chapter, we saw this definition also. So delta G is negative RT natural log of K. And remember, K is the equilibrium constant. And of course, here's the definition we just derived. Now we're going to set those 2 equal to each other, and we're going to solve for the cell potential. And when we do that, we're going to get RT over NF multiplied by natural log of the equilibrium constant. Now, this is extremely useful, relates the cell potential to the equilibrium constant, and of course we already have a relationship between delta G and both K and the cell potential. Now, just continuing at the very bottom, notice that I plugged in all of the constants. So R, the temperature in Kelvin, and the and Faraday's constant, and all we have left is N, and that's going to be dependent on the reaction. So multiplying everything together, you actually get this nice handy equation, 0.0257 volts divided by N, the number of moles of electrons transferred during the reaction, and that's going to be multiplied by the natural log of the equilibrium constant. So here is a really nice figure showing the relationships between delta G, the equilibrium constant, and the cell potential. And so we can see basically we just have three sides to this triangle, and we can interconvert depending on what our needs are. So if we have any one of the three quantities, delta G, the equilibrium constant, or the cell potential, we can calculate the other two. And any of these quantities could be used to determine whether a process is spontaneous. So we can use any of those. So let's do an example. Let's use the relationships between delta G, the equilibrium constant, and the cell potential. And so our problem is to determine the standard free energy change and the equilibrium constant for this reaction below at 25 degrees C. Okay, so there's our reaction that we're going to look at. We're going to look again at silver ions and iron metal reacting to produce silver metal and iron cations. Alright, so what do we want to think about when we solve this problem? Looking at that reaction, we can see that it's an oxidation reduction reaction. Silver plus is being reduced to silver metal. Iron metal is being oxidized to iron cations. So we're going to separate out the two half reactions. We're going to look on the chart. We're going to find their standard potentials. And then we just want to make sure that we have our equations at the ready that relate delta G, the equilibrium constant, and the cell potential. So let's work on these half reactions first. So the first thing you want to do is separate the two half reactions. So let's look at iron first. Actually, let's go ahead and look at silver first. So silver is being reduced in this reaction. And in our balanced reaction, we can see that we require 2 electrons to get 2 moles of silver metal. And when we look on our chart, we find our reduction potential, and it's 0.7996 volts. Now, let's look at the other reaction. So the other reaction is iron metal, and it's being oxidized to iron cations. And so that's going to be our reaction at the anode. And notice that we need 2 electrons to fully reduce to iron metal, or when we oxidize iron metal, we're going to get iron 2 plus cations and 2 electrons. And when we go to the chart, the reduction potential is negative 0.447 volts. Now, something I pointed out in earlier lectures, the half cell with the higher cell potential, the higher standard reduction potential, is going to be the cathode. So in this case, we can see that it fits perfectly. Whenever you see a negative standard reduction potential, be suspicious that it may be the anode. But also be careful, because they can both be negative. And then you have to look for the one that's more negative. The relationships between our variables, we have our equations down here. So the cell potential related to the equilibrium constant, and delta G related to the cell potential and the equilibrium constant. Let's get the value for the cell potential, because we need that so that we can calculate delta G. And we know how to do this already. To get the cell potential, we're going to take the standard reduction potential for the cathode, and we're going to subtract the standard reduction potential for the anode. And so 7.7996 minus negative 0.447, so this term is going to be positive. Add those two together and we get 1.25 volts. Let's go ahead and put this equation into a form where we can get the equilibrium constant value. So we want that value for the equilibrium constant. And right now, it's kind of hard to get. So what we're going to do is rearrange. So we're going to divide both sides by 0.0257 volts divided by N. That's going to isolate natural log of K on one side, and it's going to give us N times the cell potential divided by 0.0257 volts on the other side. So we're going to take the inverse log of both sides. And so you can see the result here. So there's the inverse log. E to the natural log of K is just going to give us K, the equilibrium constant, and E, this other term is going to basically remain the same. So we're going to take E to whatever the value of this is. Okay? And so you're going to plug in 2 electrons for N. You're going to plug in your self potential, 1.25 volts. And this, of course, is a constant. So you can see that here, down at the bottom corner. And we're going to take E to that power, and it's going to give us 1.76 times 10 to the 42nd power. Now, that's the value for the equilibrium constant, and notice that it is very large. And so that means the products are very, very strongly favored. So let's also calculate the free energy. And so we need our equation that relates our cell potential and free energy. And when we plug everything in, so we have 2 moles of electrons transferred per mole of reaction, multiplied by Faraday's constant, multiplied by our cell potential that we already calculated, and we're going to get negative 2.41 times 10 to the 5th joules per mole. And we notice the negative sign, so this is a spontaneous reaction. It's a good thing because our equilibrium constant was very large, and so luckily those two things line up, so we're good so far. And this is in joules per mole. After we convert to kilojoules, so just divide it by 1,000, then we end up with negative 241 kilojoules per mole. This cell is spontaneous, delta G is negative, the equilibrium constant K is very, very large, saying that it favors the products in the reaction. Okay, so the next lecture is going to cover cell potential under non-standard conditions. So we're going to look at the Nernst equation, and we're going to use the Nernst equation to do an example with a concentration cell. So that'll be the Electrochemistry lecture series part 5.